Numbers, the basic stuff of mathematics. You can add them, multiply them by themselves, any number of times. You learnt the basic rules to do that at school. Number theory is one of the oldest branches of mathematics. Back in the 3rd century CE, a mathematician called Diophantine of Alexandria introduced some problems that are still giving mathematicians headaches today. Because although the rules of how numbers behave when you add them or subtract them or when you multiply or divide them seem simple, when you start to mix multiplication and addition, things get very mysterious. Diophantine equations have more than one unknown variable, represented by a, b, x, y, and so on, and solutions that can be expressed as integers, whole numbers. Pythagoras' theorem is a Diophantine equation. A squared equals b squared plus c squared. The whole number solutions for a, b, and c are called the Pythagorean triples, and there are infinitely many of them, starting with 3, 4, and 5. And if we square them, we can see that 3 squared plus 4 squared equals 5 squared. But what if instead of squaring a, b, and c, you cube them? Not so easy to solve. In fact, Fermat's last theorem says that there are no Diophantine solutions for a to the n plus b to the n equals c to the n if n is greater than 2. And sure enough, for hundreds of years, nobody was able to find any whole number solutions if n is 3 or more, if the equation has degree 3 or higher. But it took from 1637 until 1995 for Abel Prize winner Andrew Wiles to prove that there cannot be any such solutions for any n greater than 2. One way for mathematicians to understand the deeper patterns of numbers is to represent them as geometric shapes. This is the field of arithmetic geometry. Equations can be expressed as sets of points by turning the equation into a function and plotting the solutions as coordinates. So the equation x squared plus y squared minus 1 equals 0 can be expressed as fxy equals x squared plus y squared minus 1. And then we study where this function equals 0. If we plot this on a flat sheet of paper, it gives us a circle, passing through the points where x equals 1 or minus 1 and y equals 0, and the points where x equals 0 and y equals 1 or minus 1. Any point on that circle gives us values for x and y which solve the equation. But those 4 integer solutions, which are obvious, or trivial as mathematicians would say, they are the only whole number solutions. But we can find infinitely many rational numbers that satisfy this equation. For example, x equals 3/5 and y equals 4/5 is a solution. So if you're prepared to make the numerator and the denominator large enough, there are an infinite number of rational points on the curve. They're called rational numbers not because they behave in a sensible way, but because they can be expressed as a ratio between 2 whole numbers, also known as fractions. But far more of the points on this circle are irrational numbers, so called because they cannot be expressed as a ratio between 2 whole numbers, though they may be approximated by fractions if you make the denominator big enough. If that sounds bizarre, think of the irrational number pi. Its true value cannot be expressed as a fraction, but for practical purposes, we can approximate it as 22/7, or 3.142, which is 3,142/1000. The closer we want to get to its true value, the greater the numerator and denominator need to become. This is Diophantine approximation. So that equation, x squared plus y squared minus 1 equals 0, has integer solutions, rational solutions, and irrational solutions. But if we change the power to 3, x cubed plus y cubed minus 1 equals 0, there are no positive rational solutions. Difficult equations involving both multiplication and addition can be expressed as curves in number fields. A field is a set of numbers with some rules for how the numbers behave when we add or multiply them or try to put them in some kind of order. The number field Q, for example, includes all the rational numbers. That's Q for quotient. The complex numbers, which include I, the square root of -1, form the number field C. A polynomial equation includes different powers of the same variable, like x cubed plus 3x squared minus x plus 1 equals 0. And the higher the powers, the greater the degree of the equation. And from the degree, we can determine the genus, which tells us how many holes there will be in the curve. Elliptic curves are given by cubic equations, such as y squared equals x cubed plus ax plus b. So they have degree 3. That means they belong to genus 1, and the curve, defined by f x y z equals 0, has one hole. Like a ring donut. Andrew Wiles used elliptic curves when he proved Fermat's last theorem. In 1922, Louis J. Mordell proved that the rational points on an elliptic curve are generated by a finite group of points that behave in predictable ways, an abelian group. But what about curves of genus 2 or more, described by equations with higher powers? Unfortunately, they don't follow such straightforward rules. Mordell conjectured that such curves only have a finite number of rational points, but he was unable to prove it. In 1983, Gerd Faltings proved Mordell's conjecture, which is now known as Faltings' theorem. It was a major achievement, especially for one so young, and the beginning of many important results in number theory.